Okay, so let's start this course, Astrobiology. So I'm following this book, Charles Cockell, and all the slides that you will see here. Charles actually gave me all the slides, so thanks to him. So you will see all the images and everything is from this book. It's a great book. So that's the recommended text for the class as well. Okay, so let's start this class. Astrobiology. The first thing that I want you guys to know is names doesn't matter in sciences as I think it. When you say something astrobiology, it doesn't mean it is a combination of biology and astronomy or astrophysics and that's it. It's not that. So it is much bigger than that. Planetary sciences and astrobiology, in specifically these two things, are very interdisciplinary. So you will soon see that to understand astrobiology and understanding or solving the problems of astrobiology, or even attempting to solving the problems of astrobiology, needs to bring in people from different realms of sciences, which are called departments, right? So you need people from astronomy, you need people from biology, but you also need people from geology, planetary sciences. You will see that you will need people who are doing geophysics involved in this, geochemistry involved in astrobiology, because if you think about it, living beings are what? They are like chemical factories. That's what we are, right? So in order to understand biology, we need to know a lot of chemistry. To understand the impact of different planetary bodies on us, say an impact, we need to understand geophysics or physics or astronomy, the stars that planets are revolving around. We need to understand astronomy for that, or astrophysics for that. So the idea for this course is that we all break the silos in which we are in and then come together in a class that attempts to solve these questions together. So you will sometimes have to think like a chemist while solving some of these problems, or think like a physicist or a biologist or a geologist or a geochemist. So you will have to attempt to think, at least not to solve, just to think about these questions in different kinds of with these different disciplines in mind. So forget that you are in your particular department. That could be chemistry or earth and planetary science or biology. Forget about that. Just think of it as a question that humanity is embarking on to solve. Okay, now what is astrobiology? Before looking into that, let's look into this picture. So this is a Hubble deep, like ultra deep view by the Hubble telescope. Okay, what do you think each of these are? What do you think this thing is? It's a galaxy, right? So in our universe, there are about 10 to the power 11 or like a billion galaxies in the observable universe. We have about a billion, and each of them have about a billion stars. And each of those stars in turn probably have many planets. So rough estimates brings the number of planets in our observable universe as 10 to the power 22. Very close to the Avogadro number. And in chemistry or geochemistry, we saw how large Avogadro number is. So it's 10% of that Avogadro number, 10 to the power 22. So this is like huge. This is like the biggest number that you can actually imagine in the natural world. So we cannot be thinking about astrobiology if we just think about Earth. We need to have this cosmic view in which you're thinking about all the things that are happening in our universe. Okay, so just keep that thing in mind. Like in astrobiology, we are not just thinking about Earth, we are just opening up our view to this entire universe, and we are trying to see astrobiology in this cosmic context. Now, there's another reason to think these things in cosmic context. Why? Because, okay, Earth is the only planet that we know of has life. But this is not isolated from the rest of the universe. We are being impacted by things that are happening in our solar system. The solar system will be impacted by the things that are happening in our galaxy and so on, right? So, for example, there were dinosaurs, but they were extinguished about 65 million years ago by a meteor impact, right? So, in order to understand biology, sometimes you also need to understand geophysical dynamics of our solar system, okay? So think about these things, like understanding what can impact life is also important in astrobiology. In this regard, we also have a lot of asteroid hunters nowadays. So I forget the name of this specific NASA program or like a group that actually hunts for those kinds of asteroids in our solar system that has the potential to come to us. So the idea is to protect us from these kinds of activities happening. So the meteor that actually killed all the dinosaurs was not Earth-sized. It was much, much smaller than Earth. But it still was able to destroy all the life that existed. Okay? So we need to understand solar system dynamics. That's also a part of astrobiology. Okay? We also need to understand the suns in our solar system. So any planet is very much controlled or influenced by the sun. Okay? So the solar system. So the solar system is by mass, it's 99.9% or maybe 99.98 or 97% of that entire solar system mass is the sun. So, sorry about that. What happened? I don't know what happened. Okay. So we also need to understand how the sun was formed, how it is evolving. That's a major discussion, because billions of years from now, our sun is not going to remain the same. So our sun is currently 4.56 billion years old, but this is not going to be, it's a very average sun in our solar system, but this is not going to remain the same throughout its life. Sometimes it will become a red giant, and that will affect life on Earth. So in order to understand what is happening on one planet, the astrobiological implications or astrobiology of a planet, you need to understand the evolution of the sun. The thermal budget, the energy budget that we have, a lot of that, what is the one thing that influences us the most, energy-wise? It's the sun. That is most of it. So in order to understand life, we needed to understand the sun. Okay? So there comes astrophysics. Okay? So how the suns are evolving? What is the composition of the sun? So a lot of that we discussed in chemistry of the solar system, right? So how these elements are being formed. So all the elements are forming inside these stars. Okay? It's cosmochemistry. Now, this is a very famous view it's called the Earthrise. This was taken by the Apollo 8. So this is like the view of Earth from a different planetary body, our moon, right? This is how we will be looking at different planets which have life. And this view is important because we need to see Earth as a body that has life. Detach yourself from being terrestrials and then look at Earth and then try to figure out what actually happened to this planet that made it possible for life to be present. That's the view. That's the Earthrise view. I think is important for us to like. You have to think of Earth as a planet, and it is, by the way, the only planet that we, as of now, know has life. So we need to understand how life originated on Earth. Okay. Now, there's a very typical way that life originated on Earth, right? So all life forms on Earth are carbon-based, and all life forms are water-based. Carl Sagan calls us water chauvinists or carbon chauvinists because each and every life form, be it archaea, be it a microbe, be it like trees, plants, animals, anything, any life form that you can think of is carbon-based. We do not have any other type of life form. Maybe there are other life forms in other planets, but we have a very typical signature. We are carbon-based. We are also water-based. So we are, like human beings are 70% water. Right? That's why people say, hey, drink a lot of water. Right? Because if you don't drink, so your brain is 90% water. So if you want your brain to be functioning properly, you need to be hydrated. Because if you dehydrate, it affects your brain functioning, okay? So some other life forms, maybe on Titan, maybe they are not water-based. Maybe they are, alcohol-based or methane-based or ethane, who knows, okay? So how common is a carbon-based or water-based life in the universe? That's also a question. So if we are expecting life to be present on a different planet, are we expecting it similar to what we see on Earth with a similar trajectory? Maybe, maybe not. One thing is for sure that, there's a saying, truth is stranger than fiction. Because whatever science fiction, and by the way, are there science fiction movies or TV series that you guys are watching on astrobiology, or any movie that you have watched? Yeah, Interstellar is one, but that is more on the traveling aspect, right? Is there one that is more astrobiology focused aspect? There's one called The Expanse. I don't know if you have heard. It's on Amazon Prime. The Expanse. It's on people occupying different planets. So human beings becoming an interplanetary body, interplanetary species. So Mars, there are some Martians, they call the belters. Can you imagine what the belters might be? So they are occupying the asteroid belt. So they call it the belters. And they are mining seas for water. It's an interesting one. So I think there are 4 or 5 seasons on that. There's also one movie or something like that called Life. That was also on astrobiology. Alien, the franchise, Alien. So that was astrobiology focused. So let me know what other movies or new things. It will be interesting to discuss those things in class as well. Okay. Now, what different those could be? So that is also something that we need to keep in mind. Okay. All right. The other thing is, where are we looking for to look for these different life forms? Previously, we were looking into the other planets in our solar system, right? The planetary bodies, asteroids, stuff like that. But in the last few decades, there is a new field of planetary sciences that has opened up, in which we are searching for exoplanets. So what's an exoplanet?
Not our solar system.
So those planets that are there in some other solar system, right? So there are great ways of figuring out or searching for exoplanets. And do you have a guess on how many exoplanets we have already found out?
There was a website in sometime not about
6,000, about 5,800 or 6,000 exoplanets. So a lot of what we are trying to understand about astrobiology will depend on exoplanets, because we do not have enough planets in our solar system. One thing that you will keep, we might have noticed, all the planets in our solar system are very special. Each and every one of them is special. No one is similar to the other. Is Mercury similar to anything else? No. Mars? No. Venus? No. Even when we say Venus and Earth to be twin planets, they are so different. Jupiter, Saturn, maybe there are certain, they are gas giants, but there are staggering differences. Why is that? Why do you think we have 9 planets in our solar system? All of them are very different. Because when you're forming a planet from the solar nebula, the number of parameters that control their formation are about 20. Distance from the sun, temperature, pressure, this and that. So like I'm not going into that. But there are about 20 different parameters, and you can read more about this by in the book called Planetary Crusts. It's Cambridge University, Scott McLennan, and I think Stuart Taylor Ross wrote that book. In the first chapter, they discuss it. So if there are about 20 parameters, how many planets do we have? We have 9. So this becomes a classic problem of 20 variables but 10 equations. So you will not be able to uniquely identify. So all of them will be different. That is why the exoplanets become important. Because when you have these exoplanets, you get so many of them, now you might be able to find out similar type of planets. Some unique behavior that says, hey, okay, these are Earth-like. By the way, when you read in research papers or read in the news, Earth-like planet discovered, our resolution of those planets are so, I should not say bad, but it is so limited currently that we will not be able to distinguish between a Venus-like and an Earth-like planet. So a Mars-like planet, an exoplanet, might well be a Venus-like planet. So keep that in mind. So we have done a lot of research. So we have found super Earths and all these kinds of different planetary bodies, which I'm not an expert on, but we still have a long way to go. Okay. Now, not just theoretical, not just the observation. Astrobiology is also playing a part, will soon play a part, when we are trying to make human beings an interplanetary species, if we are able to do that. Definitely we are aiming for that. So there's this book called A City on Mars that it's a good, it's a discussion on, can we settle in space or should we settle on space, and have we really thought this through? So this is written in a very light fashion, so I suggest that you read it. This will give you some perspective on colonizing space and things like that. By the way, I don't like this word colonizing, I mean settling in outer space, things like that. So it's a good book to read. Okay. The other thing is ethics of space settlement. So that is also a very important part of astrobiology. Okay, we'll get to that when the time comes. So there are different fields that come in together when we are talking about astrobiology. Okay, this concept is not new. The concept of astrobiology, this is not new. Since the early Greek philosophers have promoted this idea that in this entire cosmos, how unlikely would it be that we are the only planet to have life? It's not that unlikely. Okay, it is not that likely. So this was proposed way before. Then came Copernicus, who steered us away from the heliocentric, from the Earth-centric view to a to a heliocentric view in which he showed that, okay, in our solar system, the sun is at the center and we are just rotating, revolving around the sun. So the heliocentric view was proposed. Now, there is this thing about, so there are two approaches to think about astrobiology. One is I think it is also called the heliocentric approach, and the other is called the anthrocentric approach. I might be getting these names a little bit wrong, but I'll explain the point. The idea is, when we look at the universe, are we looking at a very average part of the universe? So when you're looking through your telescopes, are you looking at a very average part of the universe, or our position is very special? So our position in the universe is special, that it makes us look into the universe in a very special way. So we will discuss these things as well sometimes. It's a philosophical kind of a debate, but I'm not saying that the actual position of the Earth is at the center of this universe. I'm not saying that. What I'm saying is, given that we are the only planet that we know has life, the way we are looking at the universe, how common would it be for some other planet that also has life looking at the universe? Does that make sense? So that's the approach of like looking into the universe to find out life. Okay, but I'm not promoting that we are at the center. Okay, so there is this debate, like how special are we in this universe? Are there? So based on the 10 to the power 22 planets roughly that we think are there in this universe, what is the percentage of these planets that are probably habitable? And have you heard about this equation called the Drake equation?
The factors affecting habitability.
Right, or intelligent life. So look into this, the Drake equation. So that also brings these things into context. Like, okay, what is the probability that a planet in the universe has intelligent life? So that's the Drake equation. So interestingly, I was in the room where the Drake equation was actually formulated, like a few years ago. So I went to a conference. I'll tell you the story about it. So I have a picture in which of the Drake equation, I'm standing just in front of it. So Giordano Bruno is also an important person to mention here. Do you guys know about this person? So Giordano Bruno, he was burnt at the stake because the kind of ideas he was promoting at that time was considered sacrilegious at that time. So he was actually burned at the stake. And there's a public spectacle. So I think there is this statue of Giordano Bruno at the place where he was actually burnt, or maybe like in that city. Okay, so an important figure who was doing science at that time, and he was going against the popular opinion, and that's what you as scientists you should be doing. Like, you should not be scared of going opposite to popular opinion. Okay, same thing Socrates did. Like, right? So it's hard to do these kinds of things, but as scientists we need to be courageous. But there is another aspect to this. Percival Lowell was a famous scientist. He did a lot of good work. But this is what people remember him for, kind of like. So he discovered, falsely, the canals on Mars. I mean, he was convinced himself. I'm not saying that he knew that he was wrong, and he thought that he was correct. So with his telescope, he was looking at the surface of Mars, and he thought that he was looking at all these linear features on the surface of Mars, which he thought were canals on Mars. So if even in that time, did you hear the camera go off? Okay, let me just quickly check. No, it's still going on. So if you look at Mars, even with a very rudimentary telescope, you will be able to see its ice caps. That's what probably he also saw, right? And what he hypothesized was there were canals. So he hypothesized during that time, like during the turn of the 20th century, he said that okay, there is a dying Martian race on Mars. They don't have water. They have water on the ice caps, and they're building canals and feeding themselves. That's how they're surviving. So you will see there's a huge amount of science fiction novels during that time that came out, and a lot of this. And the other thing was, since they are dying, they might come to Earth and attack us. So you will also see a lot of science fiction novels based on that. But this was not science fiction, and he was pretty sure that that was happening, but he was mistaken. So that's also the flip side of things. I mean, sometimes scientists are so sure, and that scares me a little bit. I mean, we should not be 100% sure unless we truly are to objective truths. But this was this scares me. So, but truly, we didn't find any canals on Mars, right? The other thing was we were also looking at the moon, and we saw these really circular craters, circular structures, I must say. At that time, we had no idea, when people were actually learning these things, at that time people had no idea that impact cratering was a thing. So these really like circular structures were interpreted as artificial or like made through some intelligent sentinel beings, but it was not. So this was a natural phenomenon, but that was at one point of time was also proposed to be made by intelligent life. Okay, but Mariner 4 then actually went to Mars. It took like images on Mars, Moon, stuff like that. Actually saw no canals, no nothing. So there were no aliens, at least the way Percival Lowell or the science fiction novels are actually proposing at that time. It looked like a very dead planet, but we'll come back to this image later. It was very discouraging for people to look at this image, the Mariner 4, but it's not all discouraging, okay? All right. More recently, the flip side of this is that this is the surface of Enceladus, and the aircraft, the Huygens aircraft, actually saw plumes coming out from the surface. See these things? These are jets of water coming from the inside. So although the surface is icy, ice-covered, ice crust, there is water in the inside. Okay? So the Huygens then passed through this. So not the Cassini aircraft, I'm sorry, yeah, I think it was the Cassini aircraft. It went through that, collected the water, and found out that there is a bicarbonate-rich ocean there. There's also found silica, SiO2 in that. And colleagues from the Southwest Research Institute, some of these people are here who actually are actually making this discovery. So the Europa Clipper mission, which is en route, our colleagues Kelly Miller, Chris Klein, they're on these missions. Okay, so not everything is just wishful thinking. We also know that there are these planetary bodies that have huge astrobiological potential. Okay. Now, in the 1950s, 1960s, people were thinking about exobiology. So this is not like a very new concept, but what they were doing is looking at biology outside